Okay, now is Angel will talk about anisotropy in stars, physical matter, and the light in the light of the complex factor formalism. Angel, please.
Thank you. First of all, thank to the organizer for letting me show this short work, okay, and for this nice conference, okay. Today I will talk about, or I will try to summarize some basic stuff regarding this work, which is the study of some anisotropic star made of exotic matter, using an alternative formalism to complete the core of equations to solve the problem, okay? Okay. The idea is, after a short introduction, basically review the relativistic star in general relativity, and after that move to anisotropic matter based on the complexity factor formalism, which is basically a more theoretical idea, but can be applied to real situations, okay? After that, we will basically just show a few figures to summarize the main result of this short talk and the main take-home message, okay? Well, the introduction. We know that celeste bodies are not always made of isotropic fluids. So the idea is try to investigate a more general situation, okay? An isotropic star can be made of several different materials, but one of them could be theoretically dark matter or maybe exotic matter. If we want to study anisotropic stars, we usually need to clarify the equation of state and in some cases some supplementary condition to close the system. So that is usually a problem because we don't know very well how the physical inside an star. So we need to be careful with what kind of equation we use to close the system, okay? So the idea is to bypass or try to reduce the problem. We're considering an alternative formalism to complete the set of equations, which is called the complexity factor formalism, which is a supplementary relation to produced by the Riemann tensor to close the system, okay? Okay, let me briefly summarize the main idea. If you consider, well, stars in general relativity in absence of cosmological constant, you also have the same Einstein field equation, and you can consider this form of the energy momentum tensor. You, of course, taking the standard line element, you can obtain this the standard density, radial, or transverse pressure. And of course, you can recover the corresponding Thomson-Oppenheimer-Wolf equation. And well, after that, it is very, very common, okay? And after that, you can try to rewrite the energy momentum tensor in a more convenient way to simplify the computation when you try to obtain or to apply the complexity factor formalism. So we start by rewrite this term, the energy momentum tensor, in terms of these variables. And you can take the for velocity for acceleration in this way, and retaining just this value. And with help of these definitions, okay, we can, in principle, rewrite the equations in a convenient way to be susceptible to apply easily the formalism to use it to obtain the complexity factor idea, okay? Okay, with this restriction, apply for this these definitions, and demanding the standard boundary condition in this case, then the simplest case, we in principle have all the ingredients, but given that we are in presence of an anisotropic star, we need to first choose some equation of state, and also some supplementary conditions. So to introduce the idea, the supplementary condition used here, let me first give the result, okay? This is the Tolman mass, and usually you can define this in this way, and these terms appears when you decouple the Riemann tensor in a convenient way, okay? So if you remind this, normally in the isotropic case, well, the Tolman mass is basically very well known. It's a standard value. Basically, you assume that the solution is isotropic, and you don't have any difference in the pressure. All works well. But in this case, when you decouple the energy momentum tensor, you recognize that you can get situations in which the Tolman mass is the same, but you can have an isotropic situation. For instance, if P is different to 0, and this density, the derivative of the density is different to 0, these two terms can be, the sum of this can be 0, and still the solution can be anisotropic, but the Tolman mass is still the same, like the classical case. So this motivates to study this kind of situations in which, while you in principle have the same isotropic case, but you can still have some anisotropy introduced or by introduced by this term ignored in the classical case. So to obtain this, well, you first need to perform an orthogonal decomposition of the Riemann tensor. Well, they are the standard definition. I will ignore the computation right now, but you can redefine, based on this, you can redefine these tensors in terms of physical quantities of the problem, the pressure, the density, okay? And after that, you can go ahead and recognize that you have just the metric potential here, the radial and tangential pressure, okay? And after that, you can identify these scalars, and this scalar, which is called the complexity factor scalar, basically encode some possible anisotropy that you ignore in the standard case. So if you decouple this, the Riemann tensor, you identify this, and you notice why this constraint could be important in certain circumstances, okay? So if you demand that this factor could be equal to 0, so you can impose a restriction from the anisotropy factor in terms of the density. So we can use this to make progress and investigate how, for instance, the physical properties of the stars can evolve. To summarize, basically we compare the standard case with this solution in a few plots of the mass to radio profile to show how this constraint vary with respect to the standard case, okay? This is a new condition, okay? And we complete, for practical purpose, we use the Chaplygin equation of state, which is consistent with this kind of matter. And with these two ingredients, we basically solve the problem numerically. So for practical purpose, we take these numerical values, and after that, we first show using this the complexity factor formalism. I mean this restriction plus the Chaplygin equation of state, and we produce, for instance, this time of flux. When we observe, if you remember that, we observe that the evolution is well defined, but the maximum value for this figure is slightly lower than the standard case. For comparisons, we take this standard ansatz for an anisotropic star, And we again plot and produce a mass to radio profile, and we obtain this. And as you check, the maximum is higher than the other solution. And to compare them, we can observe that these three figures produce a higher profile, and the complexity factor curve is lower than the other curves. And the first one is the isotropic case. Finally, yeah, you have with this idea, you can basically predict a smaller and lighter object compared with the standard approach. That is all.
Okay. We have time for a quick question. No? Okay, well then, thank you. Let's try the speaker again. Thank you. Okay, we have